right? We're going to be working on simple harmonic motion. This is the last part of our mechanics unit. Now, it makes sense that we would finish up with simple harmonic motion because this is the motion of things that oscillate or move backwards and forwards in a regular pattern. So the reason why it's called simple we'll explain a little bit later, but for now we're going to say that the abbreviation is SHM. And the two classic examples that we're going to start with are a pendulum and a mass on a spring. So I want you to consider the pendulum here, and this here is when I've pulled the pendulum away from its equilibrium position. So I hope you can agree that it has some displacement from the equilibrium position. I further hope that you can agree that I could, if I wanted to, resolve the weight force and the tension force in the spring, and I hope you agree that there's going to be an unbalanced inward acting force. And as we know, unbalanced forces cause acceleration. So I hope you can agree that as I displace the pendulum bob from its equilibrium position, there's going to be an inward acceleration acting on it. And obviously, hopefully, as I extend this displacement further and further and further, this inward acting acceleration, this restoring acceleration gets bigger and bigger and bigger because obviously as this angle increases here, the weight force and the tension force are more and more at an angle to one another. Therefore, the resultant unbalanced force is going to be bigger and bigger. Therefore, the inward acting acceleration is going to get bigger and bigger. So let's consider the mass on a spring, and this one's harder to see, partly because my drawing's so terrible, but let's imagine this is the equilibrium position, and I've pushed the spring up, and I trust you remember from last year that if I push a spring up, I'm going to store energy in the spring. The spring is going to be pushing down on the mass to try and get it back to the equilibrium position. And I hope you can see, without me having to draw any more diagrams, that if I push the spring tighter and tighter, if I increase this vertical displacement, that there will be a bigger and bigger inward acting acceleration or restoring acceleration. I hope you can also see that if I took the spring and I pulled it down, that the spring would act to accelerate the mass back up. And as I stretched it further and further, assuming that I don't reach the breaking point, assuming that I stretch it further and further, I hope you can see that the restoring force, the movement upwards towards its equilibrium position, will get bigger and bigger. So what we're left with is a situation where we can say that all simple harmonic motion has an acceleration, an inward acting acceleration. I'm just going to move that up so you can see it a bit better. All simple harmonic motion has an acceleration that acts inwards towards the equilibrium position. And that acceleration is going to be directed away from the displacement. So remembering displacement is a vector here, so this minus sign is only telling us that the acceleration and the displacement are opposite to one another. The acceleration's towards the equilibrium position, the displacement's away from the equilibrium position. Times by some constant that I'm just going to call k for now, times by y, the displacement. And if we look over here, we can see that just like our other forms of mechanics, we have some really simple values that we use. We're interested in the displacement, where it is in relation to the equilibrium position. We're interested in the amplitude. We set that as the maximum displacement. We're interested in the period, the time it takes for one complete oscillation. So if we started here with the mass at the top, it would be from the top to the bottom to the top again, one period. And the frequency, the number of times it oscillates per second. So none of those are new quantities to you, and I think once you think about this for a little while, you'll see that this is an instinctive understanding for you. We still have to do maths about it, but it shouldn't be too hard.